Hello YouTube, in this video we're going to be looking at solving trigonometric equations that involve a little bit of factoring. And so the two types of factoring that are most commonly seen are typically going to be greatest common factor, or we could see that some of our trigonometric equations can be written, say, in quadratic form as a trinomial in what we call quadratic form. So in this video we're going to be looking at the GCF and how that would be a useful thing to use when solving an equation. So starting by considering this first one here, we have secant x minus secant x tangent x is equal to 0. And I would say that the most important thing is that we'd set equal to 0. And this is probably true almost all the time. Set equal to 0, and then, I guess factor if possible. So factor if possible, and then set all factors equal to 0. So set all factors equal to 0 and solve equal to 0 and solve. So this is going to be our method here. It's the same method we use when solving algebraic equations like these here, except for these have trigonometric functions in them. So when we look at number one here, we say, okay, well, looking at these two terms, we have secant x minus secant x tangent x equaling to 0. I notice that these two terms have in common a secant of x. So we would just factor out our secant of x out in front, and we would have to put a 1 here for a placeholder, so that if we were to redistribute, we could multiply secant x times 1 to regain our secant x here. But we get secant x times, in parentheses, 1 minus the tangent of x, and this is equal to 0. Now the benefit of doing this, of course, is we've taken something that's written as a difference of two things, something minus something, and rewritten it as the product of many things equaling 0. And because we have a factored statement equaling 0, then either secant of x had to be equal to 0, or 1 minus the tangent of x has to be equal to 0. So let's deal with these individually, starting with this one on the left here. Now, I noticed that I already have my trig function by itself, which is a primary goal of all of our solving here, but we'd say also that this is a reciprocal trig function. So one thing I do want to mention here is this, that if secant of x is equal to 0 over 1, then it would be true that the cosine of x would be undefined. And I'm actually going to write 1 over 0. So we're going to ask, for what angles is cosine ever undefined? And the interesting thing about it is, if you look at your unit circle here, cosine values are, of course, all of our x values here, and it doesn't matter what angle we go to. Every point on the outside of the unit circle has an x value. So every angle has an x value. Every angle has a cosine. So that's to say that this is no solution for this equation right here. There is no answer to this question. Now, with respect to this over here, let's go ahead and isolate our tangent here. So if we were to say subtract the 1 over the other side, we get negative tangents equal to a negative 1, so that a positive tangent is equal to a positive 1. So now solving this here and using an inverse trig function, essentially we would have, x is equal to the inverse tangent of 1. And so we would say x is the tangent inverse of 1. We say, what angle was it that when we took the tangent of it, we got a positive 1? And so essentially the first thing we'd want to diagnose is in what quadrants were we? And we say all students take calculus here. We'd say if tangent came out to be positive, we either had to be in the first quadrant here or we had to be in the third quadrant here. Now the next question we want to answer is, what kind of a reference angle are we talking about if tangent came out to be 1? Since these both have to have the same reference angle, just finding out one of them is useful here. We'd say tangent is 1 if we're at a 45 degree or pi force reference angle, because y divided by x there is 1. So we would say that this is a 45 degree reference angle, or I'm going to say a pi force. And that's true about this down here. So in terms of our solutions here, we would get, it's true that x is equal to pi force, but also equal to 4 pi force plus another pi fourth. So we get pi force and 5 pi force. And you know what? I'm going to write all possible solutions here. So we're also going to add on multiples of the period here, 2 pi k plus 2 pi k, where k is some integer. So we say here are all the solutions to this equation that we see here. Now looking at number 2, similar situation. We have 4 cosine theta times sine squared theta minus cosine theta equals 1. So what we end up with is a situation here where we've already set it equal to 0. In terms of factoring it, they both have in common a cosine of theta. So we're going to factor out the cosine of theta here. We get cosine of theta. And this is, times, in parentheses now, if we factor out the cosine of theta, we'd be left with 4 sine squared of theta. And we'd say minus 1, and this would be equal to 0. So now we can see that we have a product of two factors here. Technically, we could continue to factor this here as a difference of squares. As a matter of fact, let's go ahead and do that. We'd say, because we can, we'd say this is 2 sine theta plus 1 and 2 sine theta minus 1. Now, we could have set it equal to 0 and solved it. We'd get the same answers anyways, but let's go ahead and pursue this here. So now that we have this completely factored, we could say it's either true that cosine of theta had to be equal to 0, or 2 sine of theta plus 1 has to be equal to 0, or 2 sine theta minus 1 equals 0. So I'm going to do a little cleaning up here. As a matter of fact, with this one here, we'd subtract 1 and divide by 2. So it's very true that sine of theta is equal to negative a half. And over here, we'd add 1 divided by 2. So it's true that sine of theta is equal to positive a half. So with each of these, using inverse trig functions, we could say, well, then our angle here is equal to the cosine inverse of both sides. We'd say cosine inverse on the left cancels out our cosine, leaves behind theta. Cosine inverse on the right is just cosine inverse of 0. Over here, we get sine inverse of negative a half. And we're also going to get sine inverse of positive a half as the, not equals, sorry. Just that I forgot to write the theta, and I was thinking about writing that in there. But our angles are these here. So let's go ahead and start with where cosine is 0. With respect to where cosine is 0, that'd be where we'd have x values of 0 on the unit circle. So I can only think of 2 places where this occurs, up at pi halves and then down at 3 pi halves here. So we would say 0 comma negative 1. So our answers here would be that theta is equal to, I suppose, pi halves, and because it's a cosine function, we'll add on period lengths there of 2 pi, we'd say, and also 3 pi halves plus 2 pi k. So that's the solutions for part of our equation here. Let's go pursue the rest of these. So now we say if sine came out to be negative a half, what quadrants must we have lied? What must our angle terminate in here, essentially? So sine's negative. We know we have to have negative y values. And so we'd say that here are 2 angles. In terms of reference angle, though, we'd say if sine comes out to be a half, what angle are we sitting at? I think that's got to be a pi 6 or a 30 degrees. So we can see our sine value is a half at that kind of a reference angle. So if this is pi 6th here, pi 6th, and this is pi 6th over here, then we'd say our 2 reference angles being given will allow us to find these 2 angles here. And so we'd say pi 6 past pi, that would be theta is 7 pi 6th plus 2 pi k. And then also that we are a pi 6 short of 2 pi, so 12 pi 6 minus 1 pi 6 is 11 pi 6th here. So we have 11 pi 6 plus 2 pi k. So there are solutions there. Now checking out this last one where we say where's sine positive a half, the neat thing about this one, and I suppose I'll move this out of the way this time, is that we know it's got to have a 30-degree reference angle, and sine is positive both in the first and second quadrant. So we'd say, we know if these are both a pi 6th right here, pi 6th, then we'd say our 2 angles are pi 6th and 5 pi 6. We'd say our final parts of this solution are pi 6 plus 2 pi k and 5 pi 6 plus 2 pi k. So look for a greatest common factor, get it set equal to 0, look for a greatest common factor if you can, and set your factors equal to 0 and solve.